We often hear archaeologists mention that a certain artifact is thousands of years old. Paleontologists say a certain fossil dates back tens of millions of years. And even geologists talk about certain stratigraphic layers being hundreds of millions of years old. In those ancient times, which no one witnessed and for which there is no written record, and even before humans existed, how do scientists know the ages of these objects? Today, let's discuss this topic. Let's talk about radiocarbon dating, which is probably the most commonly heard method of radioactive isotope dating. For those familiar with chemistry, carbon is a chemical element with a proton number of 6. Common carbon atoms have 6 protons and 6 neutrons, with a mass of 12. However, there are special carbon atoms that have 6 protons and 8 neutrons, giving them a mass of 14, which is radioactive carbon-14. This type of carbon atom is rare in nature, but exists in almost all living organisms. It is mainly produced by cosmic rays. During the lifespan of a living organism, through continuous ingestion of food, the concentration of carbon-14 in its body remains in balance with the concentration of carbon-14 in the atmosphere at that time. Once the organism dies, carbon-14 begins to decay into non-radioactive nitrogen-14, with its content gradually decreasing, and a half-life of 5,730 years. Therefore, by measuring the carbon-14 content in biological samples discovered through archaeology, one can roughly infer the time of death. Samples for carbon-14 dating are easy to obtain, such as inorganic materials like carbon-containing bones, wooden artifacts, and charred wood. Its measurement range is broad, capable of dating archaeological samples from 1,000 to 50,000 years ago. However, due to the limited amount of carbon-14 in living organisms, once it has fully decayed, it can no longer be measured, resulting in a dating limit of 50,000 years. For samples dating back between 12,000 and 20,000 years, the error is approximately 70 to 150 years. For samples within 6,000 years, the error is only 30 to 40 years. Although these errors may seem small, they can sometimes be sufficient to cause misjudgment of the ages of certain artifacts. At this point, some readers may have questions. Since carbon-14 is constantly decaying and definitely decreasing, wasn't there more carbon-14 in ancient times? How do scientists know the carbon-14 content of those years? Indeed, as a radioactive isotope, carbon-14 is constantly decaying and decreasing. However, scientists can determine the original or relative content of carbon-14 in ancient samples through a series of methods and research, thereby dating the samples. First, it should be clarified that although carbon-14 is constantly decaying, new carbon-14 is also continuously produced in the outer atmosphere. This is mainly due to the action of cosmic ray neutrons on nitrogen-14 atoms, forming carbon-14, which rapidly oxidizes into carbon dioxide in the upper atmosphere and enters the global carbon cycle. Animals and plants absorb carbon-14 from carbon dioxide during their lifetime. Therefore, during the lifespan of a living organism, the concentration of carbon-14 in its body maintains a dynamic balance with the concentration of carbon-14 in the atmosphere at that time. Scientists can accurately measure the current concentration of carbon-14 in the atmosphere using modern technology, and establish models based on this data to estimate past changes in the concentration of carbon-14 in the atmosphere. These models consider various factors, including variations in the intensity of cosmic rays, changes in the Earth's magnetic field, and the carbon cycle in the Earth's ecosystem. Although there are some uncertainties, scientists have been able to reconstruct the past concentration changes of carbon-14 in the atmosphere over thousands or even tens of thousands of years with considerable accuracy. Furthermore, scientists use modern carbon standards to refine these models. These standards are samples of modern organic materials with known ages, such as measuring the carbon-14 content in different annual rings of large trees to retroactively estimate and correct the carbon-14 content in the atmosphere of that year. By comparing the ratio of carbon-14 to carbon-12, a stable isotope, in ancient samples and modern carbon standards, scientists can infer the original content of carbon-14 in ancient samples and calculate the age of the samples accordingly. It is worth noting that radiocarbon dating has a certain range of errors, mainly due to the randomness in the decay process of carbon-14 and uncertainties in the measurement process. However, through continuous improvements in measurement techniques and calibration methods, scientists have been able to significantly reduce these errors and increase the accuracy and reliability of radiocarbon dating. However, the half-life of carbon-14 is too short, only just over 5,000 years, and the content in samples older than 60,000 years is negligible and cannot be measured. At this point, we must find elements with longer half-lives for dating. Next, let's introduce paleomagnetic dating, which includes archaeological paleomagnetic dating and stratigraphic sedimentary magnetic dating. Archaeological paleomagnetic dating mainly utilizes thermoluminescent magnetism in artifacts, suitable for artifacts that have undergone high-temperature heating, such as ancient kilns, stoves, bricks, tiles, pottery, porcelain, and various magmatic rocks. Stratigraphic sedimentary magnetic dating, on the other hand, utilizes the phenomenon of geomagnetic deposition and reversal, often used for paleoanthropological sites. The Earth has a magnetic field, and this magnetic field constantly changes. Clay contains a small amount of magnetic minerals. When clay is heated to temperatures above 700 degrees Celsius, its magnetism completely disappears. Upon cooling, it acquires magnetism consistent with the local magnetic field, known as thermoluminescent magnetism, which remains unchanged for millions of years. Therefore, ancient artifacts that have undergone high-temperature heating above 700 degrees Celsius will carry magnetism consistent with the local Earth's magnetic field. By testing the samples and comparing them with data on paleomagnetic changes, one can determine the absolute age of the artifacts. This is the principle of archaeological paleomagnetic dating. However, it should be noted that this method currently has larger errors and needs to be used in combination with other methods. Another method, stratigraphic sedimentary magnetic dating, utilizes the principle that the Earth's magnetic field periodically undergoes magnetic reversals. All rocks on Earth are magnetized during their formation process, producing residual magnetism. Sediments in deep seas and lakes also contain particles carrying residual magnetism. Therefore, by detecting the residual magnetism in certain rocks or sediments in the area of the site and comparing it with the geomagnetic polarity reversal chronology, one can determine the geological age of the stratigraphic layer they are in. Consequently, artifacts unearthed from this stratigraphic layer can also be roughly attributed to this age. This method is very effective for dating paleoanthropological sites tens of thousands or even millions of years old, such as human fossils from the Paleolithic era, which are often dated using this method. There is also a method called thermoluminescence dating, whose principle is somewhat similar to paleomagnetic dating. Insulating crystalline solids, such as the clay used in pottery, contain trace amounts of radioactive substances. When subjected to high temperatures, these substances produce a phenomenon called thermoluminescence, where high temperatures cause the object to release all the stored radioactive energy and then slowly accumulate energy again. The older the age, the more energy accumulated. Therefore, by detecting the content of these radioactive substances in pottery and comparing them with the radiation intensity in surrounding soil samples and cosmic ray intensity, one can estimate the approximate firing date of the pottery. In other words, thermoluminescence measures the time elapsed since the last heating event of the pottery sample. The applicable range of thermoluminescence dating varies from 50,000 to 500,000 years, capable of measuring various materials from Paleolithic burned soil to ceramics, crushed stone, loess, and calcite. However, thermoluminescence dating is most accurate when measuring pottery. In archaeological sites, pottery shards are often one of the most commonly found artifacts, making thermoluminescence dating more convenient to use. It requires a small number of samples and has a fast measurement speed, which can be completed in just a few hours. At the same time, its measured age span is large, and it has advantages in authenticating artifacts. This makes thermoluminescence dating increasingly popular in recent years. In terms of errors, under ideal conditions, thermoluminescence dating can achieve a relative error of 5%. That is, for samples within 2,000 years, the absolute error will be less than 100 years, which is more accurate than radiocarbon dating. However, within the range of 2,000 to 8,000 years, radiocarbon dating is still more accurate. When the age exceeds 8,000 years, thermoluminescence dating needs to complement and correct with radiocarbon dating. In summary, scientists use various methods and techniques to determine the ages of ancient objects. These methods have their own advantages and disadvantages and applicable ranges, and scientists need to choose appropriate methods for dating based on actual situations. With the continuous development of technology, I believe there will be more and more accurate methods in the future to reveal the mysteries of history.